Amazing day today in CASP, actually. We learned a lot. I personally learned a lot from the keynotes and from all the speakers and the assessors. And now, unfortunately, we don't have much time during the day to ask questions, and CASP is about interactions. So all the questions are jammed into this session. All today's questions that everybody had or have or will have during the discussion could be asked now. So this is the amazing opportunity. So I will suggest a few questions that popped up in my head about proteins, about predictions, about discussions. And what is that? And then I will ask those who want only, who presented today, to come up on stage, and we'll put a few chairs there to be a panel, and also the assessors. And then we will go through those questions and discuss them, but probably on the side, here on the side and there on the side, so the slides are visible and the light is not shining on people. And because we had those once, the people were sitting like that and slides were shining all in their eyes and they couldn't see anything. They didn't see the audience, but the still discussion was quite okay, nevertheless. So let's start. And yeah, please feel to interrupt me anytime and just shout if you don't like something or if you have additional suggestions right there. No, because how many people want to come up there? Probably. Well, when they come up, then we will put, I will help too. So here, I was showing those three pictures, rather cryptic pictures for this CASP, for the protein division of the CASP. And now I will try to go through them and explain the meaning if it wasn't clear already. So the universal law of nature is exponent, and exponent is not always real. Sometimes it's imaginary, and this is the imaginary part of the exponent. It's a wave. Everything goes up in waves, and we heard the two keynotes that were on the way up. Both of them created two big waves in CASP. Early on, David Baker's method of threading through small fragments, fragment assembly, revolutionized everything, and then we had big advance. And then there were some years of so-called stagnation, or when the advance wasn't that clear and that sure, it was kind of downfall. And recently, from the first keynote, we had that amazing solved folding problem, so to speak, the prediction of the fold from the sequence. That's what I mean by folding problem. You take a sequence and then you predict the fold, and that fold matches. So that problem, what is that? Oh, okay, then, okay. Yeah, because these things popping up, when I was talking in the morning, they were also popping up, and when slides need to be changed, they don't quite change, but I guess that's okay. So now we probably are in the downturn of this wave, where progress this year, as the assessor said, was not that apparent. There was some progress, but maybe not so much. And oh, yeah, everything is slow these days in these places. So that's okay. So there should, oh yes. So basically this is the question to the audience, and maybe we're missing something. Maybe as assessors we don't do the right job, or we don't do it the right way. So is CASP at the stage of incremental progress in protein structure prediction and accuracy of self-assessment? Because this is joint session about all protein aspects, including Randy's accuracy. So that's the question to the audience, I guess the question number one. Then the question number two, so it's a monkey wrench. Somebody threw a monkey wrench in the machine of CASP, and that was actually AlphaFold. Instead of running their own group, AlphaFold 3, they released it to the community after CASP started, and it kind of messed up the experiment. Maybe it's good that it's happened, but the experiment was not clean anymore, because everybody and their mother who wanted to win just jumped on AlphaFold and started submitting sequences, and maybe they were working for 2 years and developing their great methods that they never actually tested. So that's a monkey wrench. But nevertheless, the question is real, and the question comes through, is there life beyond AlphaFold 3? Is there anything that people can come up with that would be better than what we currently have? Because it seems like the more AlphaFold 3 you run, the better your models become. So that's the monkey wrench. And then the next one, yes. So this is the antibody problem. It seems like this is a very important problem that was cracked this year. Last time in CASP, there was some progress measured in the antibody antigen prediction and maybe design because they are connected. And that's an incredibly important medical problem because many people want to design antibodies to kill whatever. If you design an antibody to kill cancer, then you are a billionaire, multi-billionaire, and the whole cancer problem is completely solved. But this is a difficult question, but there has been measurable progress, I think, on the targets. There were not that many targets, but there were quite a few, 6, 7, where some groups showed performance better than AlphaFold 3 and clearly better on these targets. Again, I don't know how accidental that is, but nevertheless, it may be worth discussion. What about these predictions? What makes them tick? What makes them work? Why are they better than the AlphaFold? I know that some of them were attempted, the answers were attempted during the talk, but maybe more crystal clear. Think about it. Why did that happen? What do you do better than AlphaFold, like in 1 or 2 sentences? So people know, and they could kind of carry on and take on from that. This is a question more about accuracy estimation. So are there any new ideas beyond AlphaFold and its derivatives? It's kind of similar. There will be a lot of questions that are similar in that sense. And there is another question related to prediction. We frequently see that predictions are straighter, more regular, and more compact than the actual experimental structure. So are these prediction models better, and how are we testing that? How are we going to test that? There are competitions in protein design now when people actually synthesize design sequences that community submits and then determine if the designs were good and accurate. So maybe there are ways to test that, and maybe some of those experimental models, because they're not structured experimental data, and those things, those coordinate sets that we use and compare with, they are also models. Maybe these models are not as accurate. At least we need to discuss that and see what the community thinks. So the other problem that remains to be solved, and it's really not solved now, is how do you pick your first model that is correct? And that comes through in every assessment very clearly. So the more AlphaFold runs you get, more AlphaFold 3, the better pool of the models you have. And you have better models in that pool. How do you pick the right one? And the community cannot do that right now very well. This is another question. There is some limit to what prediction methods and AlphaFold can do. They can predict natural full-length sequences and maybe partial segments as they are in the full-length sequences. But partial segments and some fragments, they fall their own way. So these structural changes, as also mutations, like point mutation, how would point mutation change the structure, are currently nearly impossible to predict. Are there any ideas of what to do? The other category that is very difficult and nearly impossible to predict are filaments and extended structures. And then other questions, a few questions are about the organization of the experiment and assessment, if we have time. It depends how active you guys are. Organization of experiment. This year experiment was very complicated. It had stages, T0, T1, T2. Do we need them? Do we like them? Or should we have just T0, for example, and you predict your own stoichiometry? Or you don't want to predict stoichiometry at all, although I think you should, because that's the real prediction. And final question, like for dessert, so to speak, assessment method. Criticize us. We did our work. We worked for several months very, very, very hard, day and night, but we messed up in many ways, I'm sure. And you are the community who can spot it. And then next time, next assessors will do it better. So that's basically my presentation. And if we go to the first slide and invite assessors, all the assessors, and those predictors who want to participate, actually all, if they would like to come, for those presenters on stage right now, and we can continue with this. And depending on who wants to come, we can bring more chairs, and let's say this chair. Yeah, you definitely take your chair. You look strong enough. Okay. Yes, please. Anywhere you want. Grab your chair while you still can. Yes, Dima, definitely. Please. Okay. Any other people who spoke for the groups? No? Then we have too many chairs. Okay. If you reconsider and you want to come up and shine, please do so. All right. Let's go to the first question. Anybody wants to say anything about that? What do you think about the progress? Yes.
Yeah, if nobody want to say anything, I have two provocative statements which maybe this audience can address. One is that I strongly believe that machine learning, the abilities of machine learning at some point becomes limited. When the information which can be used is no more available, then it becomes relatively weak. Not only in protein structure prediction, but in general. In protein structure prediction, what can then you use? You can use physical information from the classical biophysics. And we strongly believe this in this statement, but this is for the first time when we actually saw that it works. The second related statement is that AlphaFold 2 cannot predict rarely seen structures in the PDB. If you try to predict something which is not in the PDB, you will not be able to do it. What you get is a random structure. That's my statement. And I don't know whether it's true.
Okay, thanks for the excellent start. We also have AI discussion later.
Yeah, I just want to address that point that you made. The first point I agree with. But can AlphaFold 2 predict structures that are not in the PDB? That is this all just some kind of memorization? And I think there's two particular data points that clearly convince me that it can predict structures that are not in the PDB. The first is our CASP. We've had a number of cases where, even going back to CASP 14 and CASP 15 both, where we had things that they're very far from anything available in the PDB, in which, using AlphaFold, reliable structures were generated in a blind fashion. The second example, actually very interesting, is NMR structures. Because NMR structures were, for whatever reasons, not used in the training of AlphaFold. So we have a large number of NMR structures, which we can go back, that even if they were in the PDB at the time of training, weren't used in training. And we can also look, were there any homologs or anything like that in the PDB? And we've done that study with a few dozen different NMR structures, mostly our own, in fact. And in fact, not only does it model the structures well compared to the atomic coordinates we deposited, when you compare against the experimental data, they often fit the data better than the models that we made from the data. So in that sense, I think it's not all memorization, although I do agree memorization does impact the modeling when it's available. And it's especially important when there are alternative states, as you've also observed, where you're biased toward the state that is used in the training. So that's
Okay. Randy, want?
Yeah, but he was first.
I'd like to add a point about
Okay.
the question you just mentioned. I counter what the guy said about actually machine learning can produce a de novo structure not existing in the PDB. The reason is that machine learning AI AlphaFold mostly depending on the sequence information, MSA depth. As long as you have a sequence, even though they do not have structures in the PDB, they still can predict the interactions between those residues. However, I also think increase the size of the training data set of AlphaFold can make it work better, particularly for the right now, as Nick mentioned that, AlphaFold doesn't predict the extended structure well, non-globular structure well, or because alternative conformations, or because there's no sufficient that kind of data in the training data set to make it better, to learn that area better.
Can I follow up and ask Chan about whether there were actually new folds in the protein structure prediction data set this year? Because I didn't really see that analysis. Maybe I missed it. But that would really directly answer the question. This year, were there new folds predicted?
Okay, did we see new folds?
To be honest, we didn't do that analysis, but I have an excuse, like, because what traditionally is considered a new fold, like based on classification, is different from what is really new to AlphaFold. Because AlphaFold learn probably like smaller unit, and using coevolution, how you combine these smaller units together. So I feel it's almost like what we define as new fold from evolutionary perspective is not truly new for AlphaFold. So, but we should do that analysis. So we do have the capacity to do that. We just didn't do.
I thought Nick's questions are really good, and I sense that people don't want to address them because they're so good. So, Nick, can you get us back on your question there?
Thanks, John. This is a helpful comment, but I'm kind of warming up the audience because I'm afraid they will be dead. But very fortunately, they are not, and they are talking. And we will get back to this. But about new folds, whatever I looked at those structures, they didn't truly contain new folds. New folds are very difficult to find these days, but they contain new families, and they contain singletons with very thin alignments where you cannot find sequence homology. So from the purpose of structure prediction, they are kind of new. So indeed, AlphaFold finds something that is, like Chan said, with small segments in there. I think, yeah, we will go that, and then we absolutely have to come back to questions, because indeed they're good.
I will come back to this question right now. So I just want to put 2 points forward, and then the predictors can comment on that also. So AlphaFold is so new, you would be really stupid not to use it because it's extremely powerful. But I also feel that there is so much that is not yet being explored. We see that from our combined analysis that you can now predict like 80% of the targets. It still leaves 20% other to be predicted. I have a little bit of feeling that many predictors are afraid to not use AlphaFold because they will miss out on easy targets. So maybe one of the predictors can comment on that.
I guess, yeah, one question is like returning back to novelty and things like that is a question exactly like what sort of is being resolved kind of experimentally, right? I mean, it's I guess historically easier to get, right? I mean, like other targets. I guess antibody antigens could be potentially one exception because basically we can get this antibody structures on antibody to like stabilize other structures, whatever. So it could be totally new data, right? But I mean, like on typical proteins, you get sort of similar to what you're having before, and that's why maybe we don't see kind of like interesting questions, right, on this, right? So.
Okay, then I can come back to my question again and maybe try to answer it myself. If I'm a predictor, I will be very defensive, and I would say, well, there's nothing left to predict. If you look at the increment, we are already at the GDT 90% and above. So that little difference, maybe it's really just experimental error. And those experimental structures, they are wrong. And I'm, as a predictor, right. So maybe there is no way to make big progress in structure prediction, and everything else since this point is incremental. And I remember this kind of sentiment at some other community, some other meetings of this community where people were horrified with AlphaFold. They say, oh, we will never get any funding, we will just all die out, AlphaFold solved every problem in the world, and we have nothing else to do. But this cusp shows that it's actually not really true. The problems are slightly different. We don't want to hunt for folds anymore, and that's why we're not really doing that structure classification that hard, because that part is indeed predictable and indeed kind of solved. But there are interactions and oligomers that are completely not solved, and there progress has been made, small, so to speak, but large comparatively to AlphaFold even today. So indeed, it seems like the community needs to rejuvenate a little bit and do something about it. There are those problems that are difficult problems that I put up on those questions. And if you have any other problems where you feel that there needs to be significant progress in prediction, please speak up, because I'm sure there are many other problems related to these kinds of topics that are done very, very poorly. And now I have to just point to Chen and ask her to comment on that. What is bad? Do we see that the predictions are actually bad?
Just as I mentioned in my talk, the AlphaFold is not sensitive to any mutation or truncation of the sequence. But this is like more about like a CASP organization problem or difficulty, because such targets are probably very hard to collect. But they would like point the future development. Because for truncation, and truncation adopt a new fold, it's probably really very rare. A lot of maybe mutation kill the protein, and that's a different type of data. And then can we collect them? Then how much can we trust them? And then how should we evaluate them? Where do we even start? So that's just very difficult.
So if I understood Jan's talk, actually you showed that predictions are more accurate for prokaryotes than eukaryotes, and eukaryotes more than viral proteins. So doesn't that suggest that, we actually, I haven't looked this time, but we usually have a lot of prokaryotic targets in CASP. So we're getting an optimistic view, and we should be thinking about, boy, look at this terrible eukaryotic prediction, or this viral protein's embarrassing. I mean, what do you think?
Okay, anybody here wants to comment?
Yeah, I just wanted to get back to the point that Nick made about the, GDT is greater than 90 for most of these proteins. I think the problem is that, for historical reasons, people have used things where you can measure progress even for bad structures. And a lot of these measures top out now at this point when the models are getting better. And I think, there's been an evolution through CASP to go to harder and harder sort of assessment criteria, and I think we probably need to do that to make things move faster or to see the progress that's being made. So for instance, maybe it's time to get rid of evaluation units, and you should only predict the whole thing, and perhaps couple that with something that gives the same kind of information as the PA matrix, like which subsets of this structure do I believe have the right relative organization with each other. And we should probably also be getting more to things other than C alpha measures. Should be more, all atom torsions or atomic positions.
Yes, excellent points. And we were actually using high accuracy GDT. We already converted to that. And for many structures, we didn't use domains. We used evaluation units, so to speak. And one point I want to make, there wasn't time to make it during the assessment talk, that usually when people don't predict mutual orientation of domains accurately, that means that domains are more flexible related to each other. So that is a good point to study, but again, that comes back to the organizers, unfortunately, and the target selection and the ability to test predictions experimentally, which for mutations, and mutations is obviously a very important problem for human health, there isn't really any way to evaluate currently in the current schema.
I probably can add 2 cents to this. So first of all, I was just in touch with someone before the CASP meeting, and he told me that CASP is sampling evolution. So essentially they did analysis, and they said that 2/3 of targets that we ever had in CASP have really deep evolution, like 20 billion years. So, and 1/3 of those is just new targets, but that's good. I think that if we can get this 1/3, that's really nice, so that's half full glass. And second, it's natural selection. So you are absolutely rightly saying, that we get what we can get, and people are these days just not offering us structures that they think that AlphaFold can easily solve. So we had many of those in this CASP, but that's a tendency. So I'm in touch with many people and they say, okay, we got this with AlphaFold, we are not giving this to you. So targets will be becoming more harder in CASP, I believe, but we'll be getting fewer and fewer targets. So that's what I think will happen.
So
Okay.
I've just one, if I may, one question about folds that haven't been predicted, and that's for membrane protein folds. And that's something that I spent my whole life thinking about, and I've found many cases, whole families where I can't see a sensible AlphaFold model in there. And I think the lack of a membrane protein energy function or scoring function really makes that problem even harder. And I would really love to see the field focus on that, but I understand that I maybe need to drum up some enthusiasm by my experimental collaborators to provide you with structures.
Yes, thanks. That's an excellent point. Oh, and then we probably should go to the next question. What are you going to do beyond AlphaFold? And that was a good transition, because indeed AlphaFold was trained on what's in PDB, and it doesn't have that many membrane structures. So sometimes indeed their topology could be wrong. So any comments on this question?
No, I think we have been playing like a lot like with AlphaFold and basically like what it's doing. For example, I mean in specific tasks, like for example like modeling, say peptide interactions related, like for example, I mean because there are peptide interactions which are in PDB and there are ones which you know are definitely binding, but we don't know how it looks in PDB. And what we see that actually if we track basically like because there was a discussion now that like this time series right of the data, right, I mean is not really fair because it's still repeating a lot of known things. If you start removing it, actually the success of the model is actually not that huge. So for basically the question is that I mean like it does seems like AlphaFold cracked kind of say domain code, right? But did it crack the interaction code fully? I mean, like, so this is basically, and the question is that, is there any way faster than PDB to get this new data, right? That we can actually generate data at scale, right? So that basically could be a question, right? Because I think like we have like some, like, I mean, and then obviously similar thing, I had a kind of discussions about like ligands where there is no information on the ligand binding site, and basically there is definitely known the ligand is binding. I mean, like, it's kind of success rate of all the modeling tools are actually like is quite low, right? I mean, like, so basically there is, but the question is that unfortunately because we work, basically we get the data what people are getting, right? So if that the peptide interaction wasn't solved for, although it's well known, I mean, like from the CLM for years, and it's not being solved for now. There are some, I guess, technical problems in getting it right, and it is not clear why it's not here. But I guess here having some thoughts about it, right? How we focus on where the data is lacking and how basically what can we do, and indeed whether physics can help to reduce little bit requirements on the data and things like that. That would be a good chance, right?
So I have another suggestion for life beyond AlphaFold, maybe a greener version of AlphaFold, reducing the CO2 footprint, things like that. Now we see massive sampling, and yes, the solution is in there, and some people are able to find it, it's fine. And then you go to your average biology colleague, whatever, who see CASP results, believe all the results are solved, all the problems are solved, and is going to run these 25 models on AlphaFold and believe that what he gets is solving his day, all these problems. So I think CASP and many people here have the resource to solve these problems, but the remaining of the world might not have the resource and tools to do the same. So I think there's still a lot of improvement that can be done to popularize basically these kind of prediction methods so that the mass of researchers can use them also and get proper results.
Okay, thanks. Any more comments about how to improve? Yeah, please.
So I think in the past, in the previous class before AlphaFold, model generation is...
Mic is not working, right?
Okay. Yeah, before the class, before the AlphaFold tool was developed, model generation, generated sample model is a major bottleneck, right? Now, actually, sampling model actually is easier than selecting the best model. So I think there's still a lot of work to do can we reliably select the best model or correct model from many, many wrong models? Like antibody antigen, it's very hard to select the very good model. So I think that actually, these are two different problems. One is generating models, another is selecting them. So selecting, I think right now, is lagging behind.
Yes. I just wanted to comment on the monkey wrench aspect of this, where you said AlphaFold 3 threw a monkey wrench into things. So when I was looking at the PLDDT estimation, and I saw that 24 out of 54 groups that we were evaluating had at least some models with individual atomic PLDDTs, I started trying to find out, somebody doing something different from AlphaFold, and everybody that I asked, whether they said they used it in their abstract or not, every single one of them said it had come from AlphaFold 3. So that also makes it a little bit difficult. I think probably the abstracts were written before AlphaFold 3 was available in some cases, but we, can't count on that to evaluate the impact.
Yes, that's a whole additional problem about the abstracts. Indeed, to help the community better, the abstracts better be as accurate as possible. Please do so. We read those abstracts. The assessors read them from the beginning to the end. So just don't put the abstract that is 5 years old into there.
I have a suggestion for the new prediction category. AlphaFold predicts static structures, and static systems are dead, as we know. So life is moving things, and environment inside cell is dominated by non-specific transient interactions and ensembles of conformations. So how about, in addition to prediction of static structures or structure prediction per se, to predict energy landscapes with all these multiplicity of minima and including non-specific and ensembles. And there are experimental techniques which are emerging as we speak, which can provide ground truth for that.
So we do have on Wednesday morning the ensemble semi-disorder session, and there are two very nice sort of ensemble, continuous ensemble sorts of targets, and I think the CASP has tried to go in that direction, and we'll see on Wednesday how far we've got or not.
Okay, thanks. I guess we just go on to the next one. This is, I think, a highlight of our assessment and this CASP, the antigen-antibody interaction. And it would be interesting to condense in 3 sentences, and I don't want to dwell on this point too much because we heard the presentation. What actually made it possible? Please.
No, so in our case, the idea basically what we set up, that we felt that, AlphaFold only, it's actually it cannot sample some of the things for whatever reason, even if you do it for a long time, or if it can sample, it would be very difficult to score it. So that's basically what we thought, that actually if we use some kind of physics-based constraints to reduce all this possible conformation to some smaller amount of things, and we had previous evidence that actually we can figure out, at least we can compare them to AlphaFold generated structures and choose the one which is more confident among them, that could work, right? And that basically, I think, what happened, right? We basically sampled things differently, and it actually,
Okay, so your solution to this problem is basically sampling.
Differently, right? So
yes.
Basically not, because we showed that past CASP, we showed that actually perturbing MSA or AlphaFold 3, kind of this diffusion style of motion in the structure module would generate, by randomizing, generate some kind of variation of structures, right? But it could be that some of the antibodies, I guess it's rare, never seen before or something like that, that it's actually difficult to generate this structure randomly, right? And by doing it from another viewpoint, kind of more rationally, could sort of give it another angle. And
okay, just right. I want to repeat this again to condense it to one word, sampling. I'm not smart enough to know what exactly AlphaFold is doing, but the suggestion is that it is not sampling the right way, and probably a better way of sampling could bring up those interesting regions in protein structure. Any comments on antigen and antibody and small peptide or anything like that?
I add one comment. I concur with what Dimas said. Actually, if you can use different MSAs, different parameters, different ways, AlphaFold 2 and 3, actually we have been able to sample all the correct models for all the antigen antibody targets in this cusp, if I remember correctly. But we're not able to put all of them at the top 1, so, or even top 5.
Okay,
So,
the other suggestion that it's not just sampling, it is also scoring, and all these questions actually can be tested. You could see in your data sets of your models, whatever you generate, if there is one that you didn't submit among top 5, maybe looking at this junk will help some progress. Don't know. Again, I'm not smart enough to suggest anything here, but we have to move on. So now, not to short it, because we are pressed on time. Back to accuracy estimation. We have a long, wonderful session about that. So are there any ideas of how to do accuracy estimation better than what AlphaFold does? I don't actually see any accuracy people up here on stage. They're hiding away somewhere.
I'm here. So,
yes.
Yeah, from
You
Randy.
didn't present, though.
Randy and Lisa's talk, actually we see that quite a few methods work better than the default scoring metrics of the AlphaFold 3 or AlphaFold 2 on ranking multimers, ranking monomers. So actually, there's some potential to be better than default scoring functions of the AlphaFold 2 and 3. But not a hit or multimers is still lagging behind.
Okay, then the next one. Oh, yes, sorry.
Maybe I missed it. I thought, Randy, you said the PLDDT prediction from AlphaFold 3 compared to the real LDDT, that was actually the best or amongst the best. So, in fact, maybe to our surprise, AF3 is sort of the leader in this area at the moment.
Yes, it looks like AF3 is the leader in all areas we've seen, except antibody antigen.
Yeah, I think I said this earlier, though, but one thing I would like to see is some way to evaluate the kind of information that's in the PAE matrix. And I don't know if we want to force everybody to put a PAE matrix into their new protein prediction, but something that evaluates that.
The other more general, oh, yeah.
Hello. In CASP, so in the distribution of people, I'm more on the user side, really, not predicting anything. And as a user, the PAE is far much more useful than PLDDT. And I see a lot of the focus here on the accuracy estimation on the PLDDT. But since the PAE appeared, that was a game changer for practical applications of the models. So there should be more focus there.
Okay, thanks. So this accuracy estimation is actually very important for people, especially for experimental biologists who use AlphaFold structures or any predicted structures. Anyway, this is also another question about that accuracy. We predict those accuracies like per atom, per residue. Is it possible to do it some other ways, like the overall confidence of this interaction rather than for particular atom? What is the probability of this interaction happening or something like that? It's a difficult question. Anybody wants to?
Isn't the IPTM reporting on that?
Yes, Randy, what do you think? It's your question.
Okay. Well, I spend a lot of time talking to colleagues and training them how to use AlphaFold and how to interpret the confidence measures. And they're not bad, but people do struggle with them a bit. I don't know if there's a better way to do it, but it's worth thinking about, because the downstream users really need to know what they can trust and what they can't trust.
Okay.
As a user also, I think there is not one way of the perfect metric. It depends very much on the question that you want to address. So I think for you, if you want to do molecular replacement with models, then the PAE is very important. If I want to do mutation in an interface, I don't care about the PAE, I care on the IPTM. So it depends very much on the downstream task.
Yeah, I just remind people, and I think most people are aware, PLDDT and PAE are very related to real motion. There are correlations, at least, between PLDDT and PAE and experimental measurements of flexibility, for example, nuclear relaxation and carbon chemical shift data. So this idea of multiple conformational states and error estimates, they're kind of coupled together. They're convoluted together.
So this is a loaded question that you probably would all love to comment on. Are the models better than experimental data, so to speak? And how are we going to test that? Mark, maybe?
I have a related question both to predictors and assessors. When you predict a protein structure as a monomer, and then you predict as a multimer, do you see the conformational changes caused by the molecular interruption or not? This will be obviously an important question, whether alpha AF3 can predict something in hollow versus apo, from apo to hollow. And the protein community probably has to have some opinion already because, you know, many structures have been predicted as monomers and also as multimers in complex. So I don't know whether there is any experience and expertise on this.
Okay. Oh, yeah, there are people there.
I got a mic, yeah.
Oh, okay, sorry.
Yeah, so this is maybe a question, it's both to assessors and predictors. When I've played around with AlphaFold 2 or AlphaFold 3 for proteins, I see that often the fold is captured extremely well, but the loops aren't, and sometimes the loops that are the most interesting parts of the protein, they're in the enzyme active site, or they're the parts that bind some other protein. Those are not modeled well. Of course, they have low predicted confidence, which is nice, but I just wonder, as for the assessors, as you're looking at the targets, what would happen if you asked the experimentalists to identify the parts that they cared about the most? Would you get a different ranking, you think, of predictors? Would AlphaFold 3 be, terrible, actually? Are we back in the regime where deep learning is not helping?
Yes, these are excellent points, and indeed, experimentalists usually care about what they call functional site, and they just look at the accuracy of the model around the active site. But sometimes it's not known where it is, and sometimes it's not even known how to address this. So these are also difficult questions beyond the time of this discussion. But if anybody has a last comment about that question.
Yeah, I can comment. So I think this comes back to the question, is my computational model better than the experimental one? Of course, most of the time the computational model has very nicely defined structures, and we want it to be the better model, but in reality these proteins, they are very dynamic, and probably a lot of it is irrelevant really in the assessment. And a lot of the function is especially in these dynamic regions.
Regarding this in particular, Guy told us today about these NMR structures that then you modeled and they looked better. Did they also look straighter, more regular, more compact? That's the first question. For you?
Comment, you mentioned the parts that have poor Malprovity scores. Do you think the model in those regions is probably better
than the models generated by the experimentalists? Because the methods that are used to generate the models have flaws by interpreting distances into distance restraints. and issues about inconsistent restraints. But AlphaFold models, then when you back calculate the NOC spectra, the raw data, have better NMR-R factors. So at least for the NMR structures, or at least for some NMR structures where there's sufficient training from that regions of structure space, the models are better. They're more accurate than the experimental structures that were put in the PDB.
Yeah, thanks. Guy basically suggests that sometimes AlphaFold models are correct.
And then we saw today from you an example of an NMR structure. Then there was a model and it looked better folded. Instead, it was a kind of loop. But the people who solved that structure, I'm sure they did N15 relaxation at least, because it's something that you do just in a couple of days. And so there you have data that you could use to check if that loop is really flexible or not.
I mean, I could see. I could see from the pic. I actually, we started to talk about this, and I sent you an email about it. Probably that loop has got conformational flexibility. Probably it, in fact, isn't even very well converged in the set of NMR structures. Probably the chemical shift show that is flexible. AlphaFold is predicting one of the multiple conformations that's adopted in that loop. And we've seen that in other structures, and we published that kind of thing in a number of papers.
Okay, the last comment about this.
I actually was wondering if I could pose a slightly different question, which is, I find it absolutely amazing how well AlphaFold works, and what we're hearing now only emphasizes that. And to some degree, I guess the question is, what does it tell us about what drives protein folding to these structures? Can we get some physical insight by asking how AlphaFold, what information it's using, how it puts it together?
Well, that's a whole different question. It's a very good question, but I still want to go to this. What AlphaFold tells us that it can't pick the right model. And if it can't pick the right model, maybe it doesn't really predict something physical in many, many cases. But this is the outstanding problem for this community to solve. And maybe it should be solved by assessors not looking at the best models at all. Just first model. Maybe there are so many models and so many stages. Maybe you should be required to submit just one. That's also a difficult question. But this is an unsolved problem for you to solve for the next cast. Pick the right model. You cannot do it. Sorry, you just cannot do it. You fail. Any comments about that?
Yeah, sure. I think this is a major challenge according to my experience. So in CASP, sometimes I see a very hard target. I have a couple of alternative models to select. I really don't know which one it is. I say this one 40% chance, another one 50% chance. I think it's this question. Okay. I think that's
no. Previous.
Okay.
Because we are very short on time.
Okay. I think that's indeed I think I anticipated that there will be some breakthrough in this area, because this is the problem that AlphaFold hasn't solved. How to select the best model out of it, or select the correct topology from alternative models. This is really AlphaFold hasn't solved it. I think it's very, very important that be considered a major breakthrough. If we can consistently select the correct one, best one for those targets, then you can claim protein structure prediction problem can be largely solved. At this moment, the sampling part has been solved. Very good, but the ranking is still far from being ideal, as we can see from the...
Okay. I think you should not limit to one model. I think you should do like in Capri, ask people to submit 100 models. You can decide to assess only the first one, but you want to generate a very diverse set of different methods so that the scorers can work on it.
Okay, thanks.
A quick comment. The machine learning community has been pushing for more explainability. Rather than more models, I think it should be more explainable models.
So I want to support what Alexander said, that we shouldn't limit to one model, we should expand the number of models, and then we should assess them by their ability to match with the experimental maps, not with the structures that are modeled into the maps. And that would give us a much better way of assessing them.
Thanks very much. Would you volunteer to do that? I think we have a volunteer.
Yeah, I just want to mention, we've done just that. We've done AlphaFold sample and AlphaFold sample 2, generate large numbers of structures, then select them against chemical shift perturbation data or select them against NOE data. So you can actually use the experimental data to select the best models. And that's actually 2 papers that in bioRxiv, if you're interested in that.
Okay, thanks.
There is just one point I would like to raise here, is because I'm interested in proteome-wide or interactome-wide prediction of structure for protein-protein interaction, for example. I think CASP should also assess the scalability of these methods in terms of computational efficiency and accuracy, because when I come here and I see so many papers, and also when these methods report itself, they show amazing results because they compare to a benchmark set that we know it's a structure. However, when I apply these methods on the larger scale, like for example in the human proteome, currently we have 65,000 protein-protein interaction, and when we apply methods like AlphaFold 3 or 2 on them, we get only a few thousands that we're able to predict. So I think the method should also be assessed based on its scalability to predict novel reasonable model, even without no target or ground truth for it. Thank you.
Okay, thanks. I think we're really getting short on time.
Can I say one thing?
Yes.
Okay, so in, coming back to selecting the best models, in Capri we have now been collecting the combined predictions for the last 20 years, put that in the data set. All the assessment metrics have been calculated, and that gives about 200,000 models. Now, this CASP alone, we have 500,000 massive fold models, and I'm pretty sure that everybody will be using those because the assessment metrics of all of those models are or will be available. But I am very curious to see if that will work in CASP, on the CASP targets in 2 years' time.
Okay, thanks very much. I think we're really getting
I also want to say something. I of course like just one model, but I think that to make a minimum change and to make the experiment more effective, we can have 2 phases. So in phase 1, people still submit 5 models or even 10 models. And in phase 2, we ask all the people to select from the pool of submitted model to select the best one. And then we see like how they all ranking from the same pool. So then we separate the sampling and the ranking problems into 2 phases. That's probably not too hard to implement.
Oh, okay, thanks very much. We have a few questions left, and we cannot go through them because you need to go to dinner. I could stay for this whole night if you want, but nevertheless we have other discussions, and some of those questions might be important for those other discussions. For example, about assessment, there will be a predictors meeting, and there will be other opportunities to answer them. And if anybody wants to pose or say something, pose a question or say something really, really important about this, now is the time. Okay, looks like everybody is hungry, and then thank you very much. And indeed, the progress is absolutely amazing, but yet there are many things to be done. For example, model selection. You don't do model selection well. You just don't. Sorry to say that. The progress is incremental. Yes, it is incremental, except maybe one that Dima and Shandar will be talking about, antigen and antibody prediction. And then there are many other ways to adjust this experiment to do it better and to serve the community of the future better. And thanks very much.